Hello, everyone. Mr. Minix, my name. Math is my game. Today, here we are starting Chapter 7 in my Algebra 2 class. And the title for this first section, it's a big section. We're going to cover this over the course of 2 days. So lucky for my class today, there's not going to be any homework over this tonight. Although I could hand it out and assign it, I'm not going to. But exponential functions. So we're going to explore the particular form. Exponential models, so we will be talking about how to write one of these. And that's the primary objective from this lesson, is to be able to write one of these exponential functions or models. And then a second part to this that's not included in the book for some strange reason is the compound interest formula. The book puts it in between two sections, and then they expect you to know it as if it's in a section. So that's why we're going to spread this out over the course of 3 days. So Chapter 7 is all about exponential functions and their inverses. And I'm going to have to pick up some missing information at some point along the way, and we will. But anyway, the first thing we're going to look at today then is the form. The form, whether you like y equals or f of x equals, the form of one of these exponential functions, go ahead and change colors here. It's a multiplied by b, and the b is raised to the xth power. Okay. So whenever we write a function, there's always a y in it, there's always an x in it. And in this case, the form of the function is a times b to the x. Okay, that's the form. And what we'll see over the series of the next few graphs, is that a and b, whatever they are, they're going to affect the graph. And we'll try to make some conclusions or draw some conclusions about how a affects the graph, how b affects the graph. And I don't want to give too much away just yet. I don't want to say, what a could be or couldn't be, or what b could be or couldn't be. The restrictions are really important, and I think on the first quiz over this on Tuesday, I might actually ask you what are the restrictions on the variables. If not on that quiz, definitely on the last test that we have over this material. Okay, so examples of graphs and their parts. The first one we're going to look at, and I'll do this on the TI Inspire. We'll go Doc, Insert, and I'm inserting a graphs page. We're going to look at 2 times 3. Whoop, let's try that again. 2 times 3 to the x power. 2 times 3 to the x power. And that's going to show up in blue, so I'll write it in blue over here. So y equals 2 times 3 to the x power. So when I go ahead and graph that, there's a couple things I want you to notice. I want you to notice from left to right, does that graph increase or decrease from left to right? What'd you say? Increase, good. And when it's increasing, there's a couple of words that we throw around with exponential functions. We say that the function either represents a growth function or, and I'm going to set this up to infinitely clone because we're going to be dragging these, either growth or decay. So because it's increasing, what would you say that function's doing, growing or decaying? Growing. So this represents exponential growth, okay? So for y equals 2 to the x, it represents growth. And for each of these, I think it'd be good if we noticed what the y-intercept was. So let's take a look at that graph one more time, and let's see if we can see that graph's y-intercept. Can anybody spot it? The value of y when x equals 0, where the graph goes through the y-axis. Is it 2 or 3? It's 2, right? If I go to the table, Control T, it's the value of y when x is 0. So our y-intercept is 2, right? All right, so our y-intercept here then is 2. So let's look at another one. Let's just switch the A and the B around for a minute. So I'm going to get rid of my table. I'm going to go ahead and just add a new function here. 3 times 2 to the x. So all I did was switch the A and the B around. So is this one growth or decay? This one's also growth. So for this next one, y equals 3 times 2 to the x. It's also growth. And let's see if we can find the y-intercept of that red one. Can you see it? Oh, it's 3 this time. The y-intercept here is 3. Remember, y-intercept is the value of y when x equals 0, so technically it's a point 0, 3, or occurs at that point. Is it safe for us to draw a conclusion then about either the a or the b value? Can you draw a conclusion yet? Can you say something about a or b? A is the y-intercept. There you go. Nice. Good job. A is the y-intercept. So A is the y-intercept. So in other words, if you ever have to graph one of these, once you see it written in its form, the graph is always going to go through the point 0, comma, A. Maybe we should make A 0 and see what happens. You want to make A 0 and see what happens? Let's see what happens if we make A 0. So I'll get rid of these. So I'll go back to that first one and I'll make my A value 0. Whoa! Can you see what happened there? There's no slope. It's the x-axis. It's a horizontal line. That's not very exciting. Does that look like an exponential function that's growing or decaying? No. So there's something in the restrictions then that we got to go back and pick up. And we got to say something about the restrictions. The restrictions, we had better say that A cannot equal 0. Because if A equals 0, we just have the x-axis. We have a horizontal line when y equals 0, and that's not exciting. Everybody on track so far? Is this making sense? Good. Well, let's look at another function. Let's see if we can change this up a bit. Let's just look at 3 to the x. Let's just look at 3 to the x. So when we have just 3 to the x, change colors again here, y equals 3 to the x, does that represent growth or decay? That represents growth. Okay. Now, what's the y-intercept of that function? I'm hearing 3, I'm hearing 1. It's one of them. It's 1. If you're not sure, look at the table. The value of y when x is 0, the y-intercept here is 1, right? Okay. So the y-intercept of this one is a point 0, comma 1. But I don't understand. There's no a value there. Or is there an a value? And it's implied. It's implicit. It's 1. It's the coefficient of the 3. And there's really, even though we don't see it, let's look right here for a minute. Let's look right here for a minute. Right here. There's really a 1 there, isn't there? Okay. All right. So we've seen some exponential growth functions. I want to see a growth function that doesn't really grow so fast. I want to see an exponential growth function that doesn't really grow so fast. So I know a thing or two about these, so I know how to make it so it doesn't grow so fast. Does anybody have any ideas what I could do to get an exponential growth function that's not going to be growing that fast? Make it go what? A decimal? Good try, but not quite. Well, I guess a decimal's okay. So this b value is 3 in its growth. The b value is 2 in its growth. What do we want to try to make that b value? As small as possible? Well, let's make it 0 and see what happens. Oh, that's the x-axis again. Dang it. Shoot. So we already said that a shouldn't equal 0. We better go ahead and say b's not allowed to equal 0 also, right? Because if either one equals 0, then we have a horizontal line, and that's not very exciting. That's not an exponential function. So here we are. We're trying to get this thing to grow, but not very fast. So how can we make this exponential growth, but not very fast growth? What do you want to try for the b value? A negative? I wouldn't, but let's try it. You want a negative. Negative 3. Oh, that's something different there. So maybe we better stick with positive values for now. So I want this to be growth, but I want it to grow less rapid as that. So what should I try to make the b value? Somebody said a decimal earlier. Let's try to make it 1. Let's see what happens if we make it 1. 1's a good number. Oh man, we have a horizontal line again. Dang it. That's no fun. So in addition to b not allowed to equal 0, b shouldn't equal 1, because if it equals 1, then we've got a horizontal line. So the interesting thing is, let me get my fanciest marker I have. I could use a paintbrush, I could use a crayon, I could use a highlighter. What do you think I should use here? The paintbrush or the crayon? The crayon? There we go. So the number 1 here is a very critical number when it comes to the b value. Everything hinges around 1, literally. Watch this. Watch what happens if I change that b value and take it from 1 to a number really close to 1, but just a little bit bigger. Now, you probably can't see it, so let me make it a little more easy to see. Let me try this. Oh, try one more time. There we go. Do you see how that's now increasing? But not so fast. But it is increasing, right? Okay. So that one is y equals 1.01. So when we have y equals 1.01 to the x, that still is growth, and its y-intercept is still 0, 1, but it's growth, and it's, let me get these growth and decay things out of the way. Got in the way there for a minute. The infinite clone thing. But it's growth, but it's really slow, or really gradual or slow growth. So if our b value is slow growth when, if our function's slow growth when the b value is a little bit bigger than 1, how are we going to make it slow or gradual decay? How are we going to make it gradual decay? Not a negative. Don't think about a negative. What did I say a minute ago? What did I get the crayon out for? I got the crayon out because everything hinges around the number 1, right? So what do I want to make the b value to get something that's going to represent a very gradual or slow, whoop, dyslexia strikes again. Slow or gradual decay. What would I need to make my b value? 2, we already saw what happens when the b value is 2. Make it close to 1, but not what? Not going over 1. So a little less than 1. So like 0.99. Let's try it. 0.99. So let's see. 0.99. Hey, there it is. That did it. Nice. Good. Huh. All right. So I'm think I'm starting to understand this. So let's look at one more. Let's look at one more. Last function we're going to look at, and then we'll draw some conclusions. I'm going to use pineapple yellow here. So let's look at y equals pi. I wonder if we could even do that, if we could use an irrational number as an a value. Pi times the quantity 1 over pi, that's going to be like 1/3. That's going to be like 0.33333 to the x. I wonder if we can even do that. And if we can, that's going to help us figure out our restrictions, because those are both irrational. They're still real, but they're irrational. I wonder if we could even do that, because sometimes you can't even. And actually with this, we're not evening. We're irrationaling, if that's a word. So we have pi times the quantity 1 divided by pi. Notice I'm using pi off the pi button. And I'm raising the quantity of 1 over pi, which is a fraction, which is a number equivalent to like 0.3, give or take. And I'm raising that to the x power. And hey, look at that. It's exponential decay. And it's pretty rapid decay, because the decay rate's about 67%, and that's another story we'll talk about in a minute. What's our y-intercept here? 3.14 approximately, or pi. Oh, I didn't do that. Okay, so in this particular instance then, again, one more time then, so this is decay, and our y-intercept is 0, pi. So to make some conclusions then about these restrictions, A and B are real numbers. So it's okay if we use irrational numbers. It's okay if we use integers. It's okay if we use fractions or decimals. As long as A and B are real, we're good. A is not allowed to equal 0. B is not allowed to equal 0. B is not allowed to equal 1. This reminds me of a song by that one artist, if you want to say artist, by Nikki something or other. That Bees in the Trap song. What's the name of that song, the Bees in the Trap? Is that the name of the song? Bees in the Trap? Okay. All right, so we've seen some examples of the graphs and their parts. We've drawn some conclusions about A. Now it's time to draw some conclusions about B. Let's say this. The function represents exponential growth when the B value is what? Remember our crayon. Over 1. Awesome. Good job. When the B value is greater than 1. Good. Can I give you a shout out? Shout out to Trinity Syvertson. Brought her A game today. Good job. Okay. Let's say something else. The function. This next one's tricky. You got to be careful, because there's an interval that people have a hard time wrapping their finger around. The function represents exponential decay when I'm going to notice how far over I'm going to slide the B. There's an interval here, so we need a high value and a low value. B's got to be between two things. Between what two things? What you said? 1 and 0. You want me to give you a shout out? Shout out to Matthew Crawford. Brought his A game on today. Good. So that's pretty important. If you're dealing with something and the B value is bigger than 1, it's going to be exponential growth. If the B value is between 1 and 0, it's going to be exponential decay. Now, there's something that I left out here. And this is something that I argue with an esteemed colleague of mine about. You notice how earlier I said I wanted to keep the a and the b values positive? When you make the a value negative, it kind of changes things. So for now, I just want to concentrate when a is positive. And so what I'm going to say then is I'm going to add a huge asterisk. So I need a creative pen for this one. I'm going to put my star pen here. Okay. So this is only true. This is only true when a is positive. This is only true for positive a values. Now, when we start talking about modeling these things, this will make a little bit more sense, if it doesn't make any sense yet. So the whole thing about b being greater than 1 is growth, and b being between 0 and 1 represents exponential decay. That's the case whenever our a value is positive. So what I'd like to talk about next has nothing to do in this context with Ashton Kutcher or Tyra Banks or Ertl. You guys know what Ertl is, right? So what I want to talk about now is modeling. Modeling. That's just a fancy way in mathematics to say writing an equation for a situation. In math, all modeling means is writing an equation for a situation. So there's a new form that I like to use. When we go to model, there's a new form that I love to use. And instead of writing y equals or f of x equals, a lot of times we write a of t. Now that doesn't mean a times t, okay? It doesn't mean a times t, so don't get that twisted. It's a of t. And what the a stands for is the amount of something. Whether that something is money, whether that something is a radioactive substance, whether that something is frogs, whether that something is water. It's the amount of something that is growing or decaying exponentially over a period of so much. What do you suppose t stands for in this context? Time. Awesome. Good. So t stands for time. Okay. Usually, in almost every problem we work, usually time is in years if not specified. Okay? So if the problem doesn't clearly state this is every second, this is every minute, this is every 6 months, this is every 3 months, you can safely assume that it's over, that each t value represents one chronological year. And for the sake of simplicity, we never worry about leap year. Even though leap year happens, we don't worry about it in the context of these. Okay? Because it is just a model, and models aren't perfect. So a of t equals, we're going to go with a again, but I'm going to call it a sub 0. I'm going to call it a sub 0. And we'll talk about why I called it a sub 0 in a minute. And rather than writing b, I'm going to write an expression. The expression is going to have a 1 in it. Remember earlier I had the crayon out. I said everything hinges around the number 1. I'm going to go ahead and say 1 plus or 1 minus. You're only going to pick one. You can't use both at the same time. That doesn't make any sense. But I do want you to see this form. 1 plus or minus something. Now earlier with the example with the pies, I mentioned the decay rate being around 67%. You remember that? The decay rate. What's a sensible variable to describe rate? R, good. That's the thing I like about math. In math, everything we use is chosen for a reason, and usually it makes sense. So a sub 0 times the quantity of 1 plus or minus r, and all that quantity, instead of being raised to the x power in this context, is going to be raised to the t power. Okay. So just to clarify some things, a of t is the same thing as your y. That's the same thing as your f of x. A sub 0, I'm moving things around that I don't want to move around. A sub 0 here is the same thing as our a value. Okay, so the same restrictions apply. 1 plus or minus r is the same thing as the b value. I'm going to give you a quiz on Tuesday, and you're going to have to come up with the b value on your own. When my advanced class took this quiz, the ones who didn't understand it, they messed up their b value. And if you mess up the v value, there's no chance of getting anything right. And then in this context, the t value, that's the same as our x. Okay? Are there any questions up to this point? Okay, so what I'd like to look at then is that the fact that the b is 1 plus r, if we're talking about growth, and the b value is 1 minus r if we're talking about decay. So anytime you're given a story problem and they mention something depreciating, they mention the word depreciation. Heard that just the other day ago, huh? Just yesterday, in fact. Anytime you hear the word depreciate, or a population might be declining, anytime you hear those words, you should instantly think to yourself, self, this is exponential decay. Self, I need to use 1 minus r to find my b value. For exponential growth, we're talking about a population increasing. We're talking about a home appreciating in value. Appreciate in this context doesn't mean thank you very much, I like what you do, I'm so glad you're in the world. In this context, appreciating means to increase in value. How are we doing so far? So there's a topic that, shame on me, I always drop the ball and I never, ever, ever talk about it. I want to talk about a sub 0 for a minute. A sub 0. That is the amount of stuff. I don't like the word stuff. Mrs. Carlson hates the word stuff. But a sub 0 is the amount of stuff we have let's see if we can figure this word out. That's the amount of stuff we have when? When time is 0, when no time has expired, when we start off the thing, when we begin the model, the moment that the model begins. There's a word I'm looking for here. It starts with a vowel. Available? No. Good try, though. In the beginning. In the beginning. Initially. Initially. I hope I spelled that right. So a sub 0 means the initial amount of a substance, the amount of a substance that I have when things begin. So suppose we're talking about, and too bad one of our students in this first period class isn't here because this would be right up her alley. Suppose we're talking about mealworms. Suppose our mealworm population is decreasing pretty fast because we have pet lizards. And the pet lizards like to eat the mealworms. So here's a model. The amount of mealworms that we have over the course of time, A of t, is going to equal, now I need to know how many mealworms I start off with. Usually when you buy those things, you buy a dozen at a time. So maybe I'll start off with 3 dozen. How much is 3 dozen? 36. I have 36 initially, and suppose that they're decaying, and this model probably isn't going to make a whole lot of sense. Maybe it could if I pick an integer for my b value. Maybe I want the population to be cut in half. So I want it to be decaying. So maybe I'll make this 1/2 to the t power. So what I'd like to know then is over the course of, and in this context, we'll specify that 1t equals 1 day. Okay? So every t value is 1 day. So let's think about something. On day 1, the number of mealworms we have. Actually, on day 0, I should say. Dang it. And on day, actually, well, let's do this. Let's do a table. Day, number of mealworms. So the 0th day, the 1st day, the 2nd day, the 3rd day, the 4th day. So the 0th day, if you're not sure about the math here, I'm going to make this as clear as I can. We'd have 36 times 1/2 to the 0 power. What's 1/2 to the 0 power really equal to? Not 0. Anything other than 0 to the first power is, or to the 0th power is 1, right? So this is 36 times 1, right? Because this equals 1? Yes? Okay. So on day 0, how many mealworms do we have? We have 36. When no time has expired on the beginning day, we have 36 mealworms. After one day, let's see how many mealworms we have left. It's going to be 36 times 1/2 to the first. So that's 36 times 1/2. What's that going to be? 18. What's going to surprise the holy heck out of you is what happens next. Maybe it's not going to surprise you. I don't know. Anybody think they know what's going to happen next? It's not going to go back up. 1/2 to the second, good, which is going to be a quarter. So it's going to be 36 times 1/2 to the second, which is 36 times a quarter. And we know that when the Germans are mad, what do they say? 9. Mad Germans. So I think once we get 2 or 3 of these established, we start to see a pattern emerge. And we know what's going to happen now. We started at 36, and then it went to 18, and then it went to 9. So what's going to happen next? It's cut in half each time, right? So now we just need to know what's half of 9. 4.5. Now, I don't know about you, but if I was a lizard, I wouldn't want half a mealworm. And then when we get down to the day 4, how many are going to be left? 2 1/4. Awesome. Good. 2 1/4, or 2.25 if you prefer decimals. And then when we get down to the 5th day, we're going to have 1 1/8. And when we get down to day 6, oh man, half of 1 1/8. 1 1/8 is 9/8. So half of 9/8 is 4.5/8, or 9/16. Maybe a better way of thinking of it. 9/16 of a mealworm. How much is that even? It's a little more than a half. Do you see why people go to the pet store once a week? Man, that first day, that mealworm's having that lizard's having a blast. By the end of the week, that thing's starving. Starving Marvin. Maybe that's a good name for the lizard, Marvin. At what point are we entirely out of mealworms? Are we ever entirely out of mealworms? Let's take a look at the graph of this thing. This is fascinating. And there's a public service announcement that I'm going to wait until another day to share with you about this. But I just want to look at this mealworm model. So we started off with 36 mealworms. And each day, Starvin' Marvin ate half of them. So 36 times, oh dang it. 36 times, where's times? Times 0.5 to the x. I got to use x on here. So what I want to see is when I'm completely out of mealworms. Now, after 10 days, I'm down to 3/100ths of a mealworm. After 2 weeks, I'm down to 2/1000ths of a mealworm. After 3 weeks, I'm down to 1.7 times 10 to the -5th mealworms, but I still got a leg left. After 4 weeks, I'm down to 1.3 times 10 to the negative 7th. Am I ever entirely out of mealworms? Okay. So something that we probably ought to say about the graph then is when we graph something like this, whoop, we started out with a whole bunch of these things, 36, and they're decaying at a rate of 50% per day. Woo! So what happens, it's very interesting what happens here. Does anybody know what that's called whenever we have a graph that gets really, really close to a line but never touches or crosses that line? We studied this in chapter 8. It's not funny, but it is. An asymptote, good. So this is an asymptote. So when we get into graphing these things, we'll see that there's asymptotes. Okay, we'll see that there's asymptotes. So the last thing, and we'll end with this today, last thing we're going to look at today is we'll talk about rates. Rate of decay, rate of growth. Rate of growth. Taken from our b equals 1 plus r, if you want to find the growth rate or the rate of exponential growth, what you need to do is solve this equation for r in terms of b. So if we do that, we'd subtract 1 from both sides. So r is b minus 1, but r is usually given as a percent. So here's the deal. The rate of growth is going to be b minus 1 with a percent tacked on the end. And to make it a percent, we need to multiply it by 100. Okay. So this is pretty important stuff here. In a story problem, you might be given the growth rate, or you might be given the b value. You might be given the whole equation. And you're going to be asked, what's the rate of growth? And we'll practice this tomorrow. That's where we'll resume things on tomorrow. If we're talking about decay, the rate of decay, and I'm going to put an asterisk by these because these are the ones that people always struggle with. We know for decay, the b is 1 minus r. So what we got to do is solve this equation for r. So I might add r to both sides. So I would have r plus b is 1. And then if I wanted r by itself, I'd have to go ahead and subtract b from 1. Subtract b from 1. So the rate of decay then, I have to multiply by 100 to make it a fraction, or to make it a percent. That's going to be 1 minus b, like that. Okay. So the quiz that you're going to take on Tuesday is going to have all kinds of problems. It'll give you an equation. It'll say, does this represent growth or decay? Or there might be another one that says, okay, if there is a 50% growth rate, what's the equation going to look like? If there is a 100% growth rate, what's the equation going to look like? So I think that's enough for today. Anybody have any questions, comments, concerns, short debates, long debates, shout outs? Shout out to my second period class. It's been a minute since you've watched one of these videos. Shout out to those of my sixth period class who are watching this video back on their own time. See you. Good. Have a nice day.